So this diagram will be used for the deriving the centripetal acceleration formula. So if you ever need to go back and revisit this diagram, you can do just by clicking the start of the video. Now, onto the proof. So by using the right angled triangle in the diagram, now I'll actually go back to this, but this is the right angled triangle. The one that's going to be re-highlighted in green, so that's the right angled triangle. We can say that S, the displacement undergone, is r cos omega t plus r sin omega t as a position vector. We're looking for acceleration, so if we differentiate twice to get d2s by dt squared, so the second derivative of position with respect to time, firstly, if we differentiate first, so we get the first derivative of position with respect to time, which is velocity. Using the chain rule, the derivative of cos is minus sine, and we bring the omega out, we get minus omega r sine omega t. There actually should be vector symbols here, so I and j. And then the second one, the derivative of sine is cosine, but again, we bring the omega out for the chain rule, so we actually get omega r cos omega t. So if we differentiate again, the derivative of minus sine is minus cosine, but again, we bring the omega out, so we actually get minus omega squared r cos omega t. Derivative of cos, we already said, is minus sine. So bringing the omega out again, we get minus omega squared r sine omega t. Now, we will get onto this slightly more, but this motion is simple harmonic because the acceleration is proportional to the negative of the displacement undergone. But how we get from this to minus omega squared s is we know that s is r cos omega t, which should be I plus r sine omega t j. And we're seeing that a is minus omega squared r cos omega t I minus omega squared r sine omega t j. So if we factor a minus omega squared out, we get r cos omega t I plus r sine omega t j. Now, r cos omega t I plus r sine omega t j is actually just displacement, so we get that the acceleration is minus omega squared s. However, this is actually the vector form of our acceleration. Because minus omega squared is a constant, we're actually multiplying through by a vector. But we actually need the magnitude of the acceleration. So if we take the magnitude of the acceleration, the minus signs disappear. We get the square root, or the magnitude of a, is the square root of omega squared r cos omega t squared plus omega squared r sine omega t squared. So if we bring the algebra terms and the trigonometric terms out, we get that it's omega squared r squared under a square root. So actually these guys cancel. And then we get sine squared omega t plus cos squared omega t. Now, there's a trigonometric identity that says sine squared theta plus cos squared theta is 1. So even if theta is omega t, this statement will hold true for any angle, which gives us that our centripetal acceleration so far is omega squared r. However, we know that v equals omega r. So if we write that as omega is v over r, we get v over r squared times r, which is v squared over r. So a is v squared over r, which equals, and I'll write it as r omega squared. So that's our centripetal acceleration derived. And then, of course, since F equals ma, the centripetal force is therefore mv squared over r, which is mr omega squared, just by putting an m in front of it. However, we can also show that the velocity is perpendicular to the displacement vector at any time. So to show that the velocity is perpendicular to the displacement vector, we have to have the dot product of the two vectors equal to 0. So if we bring back our velocity, which is ds by dt, and displacement, which is just s, we get that the I components are multiplied together. So minus omega r sine omega t times r cos omega t. plus omega r cos omega t times r sine omega t, which gives us omega r squared sine omega t cos omega t plus omega r squared sine omega t cos omega t. So these are actually the same thing, but negative. Or one of them is negative and one of them is positive. So therefore, they add to be 0. And of course, if the dot product is 0, the angle between them is 90 degrees. So therefore, we have indeed shown that the velocity is perpendicular to the displacement. So to recap, the centripetal acceleration of an object moving in a horizontal circle can be shown to be a equals v squared over r, which is omega squared r, and the acceleration is directed towards the center of the circle. Since F equals ma, we can also show the centripetal force of an object, F equals mv squared over r, which also equals m omega squared r.